Hello and welcome to IEEE Soft Robotics podcast. Hello, Professor John. Thanks so much for joining us in the podcast. I would like to ask you first how you would like to introduce and define yourself for the audience who first time listening to you.
Yeah. Well, let's see. I am a roboticist.
Yeah.
I feel like the luckiest person in the world, the things I've gotten to work on in my career.
Yeah.
And I feel like I'm still working on my PhD thesis that I started back in 1987. So for 33 plus years, I've been working on my PhD
Yeah.
thesis, which is the problem of SLAM, simultaneous localization and mapping. So how a robot can build a map and use that map to navigate. I think I feel really fortunate to be, when I started my PhD with Hugh Dorrant-White at the University of Oxford, I was one of his first two students. And it was a time in robotics when some pieces were just coming together with like representing uncertainty and trying to have robots that could do real-time estimation on the robot of its position as it moved through the world. And so even though we didn't have computer vision, very much capabilities then, and had to use sonar, we were able to draw some techniques from the literature like Smith, Self, and Cheeseman and Rajesh Chatila's work from Lost in Toulouse, where we tried to think about how a robot could navigate in the world using the kind of geometry of the world as kind of beacons, as navigation beacons. So using objects in the world and walls and corners and corridors and doorways. And so I fell in love with the SLAM problem, even though we didn't quite call it SLAM then. I called it simultaneous mapping and localization in my thesis, which if you make an acronym is SMAL, SMAL. Small is not a good acronym for the biggest problem in mobile robotics of the 1990s. So anyway, I'm a SLAM person.
Yeah.
Proud to be.
Yeah, we already know you are one of the pioneers, and yeah, you are a great robotist as well. So such an honor
Thanks, you're too kind.
have you. Yeah, but maybe before going to that, because I think it's very interesting what you mentioned the story. I'm curious about your childhood. How was your childhood was for being interested in science and technology as a kid? Yeah.
Yeah, I'm very fortunate. I grew up in Philadelphia, in Northeast Philadelphia. My father was a plumber, my mother was a secretary, and we had 5 kids. And I went to some local schools parochial schools where I had some very strong math teachers, and they pushed me. And then I got to go to a great high school that had a very strong math and science program. And as a child, we wandered around in the woods near our house, and we built forts, and we played in the river, and we did all sorts of crazy, almost dangerous things, but we explored the world. And so I feel like actually the mascot of my high school, LaSalle College High School, is the LaSalle College Explorers. I feel like I'm an explorer, and we want robots that can explore. I was a young kid exploring the world.
Yeah, that's wonderful. So I'm curious because you mentioned that you are one of pioneers in SLAM, and I think when you are at a PhD student and you're still working, as you mentioned, extension, what he has been doing since then, 30 years now. I'm curious about the start, about what's the first robot you built, if you remember, what kind of thoughts? And we know it's when you have something completely new, it's risky sometimes when you have new idea and you have never have any literature in this case. So how was it start for you to start building a first robot? What kind of question had you in mind when you were a student? That's maybe the first step. We can go further for that.
Right. Well, I'm really fortunate. There's this saying, if I've seen further, it is because I stood on the shoulders of giants. And there were giants like Rodney Brooks and Hans Moravec and Rajesh Chatila. Actually, for me, when I was in college at the University of Pennsylvania in 1985 and 86, I got to work at a General Motors factory in Wilmington, Delaware, where they were rebuilding the factory to enable robots to move the car bodies being built around. And I worked in the paint department where we were installing robots to spray paint the new cars. But I also saw that they had to completely knock down the entire plant and put in a special floor with wires buried in the floor for what they called them AGVs, autonomous guided vehicles, automated guided vehicles, to follow the wires in the floor. And this was in 1985. They're spending all this money, and all these workers can't work because they have to knock down and rebuild the factory. And I said to myself, why can't the robot just navigate like people navigate, using the naturally occurring structure in the factory? And so that problem actually motivated me when I was still an undergraduate before I got to go to grad school. But I kind of wanted to work on that problem. And it was really fortuitous. I got a fellowship, the Tehran Fellowship, to go to the UK. And it was, my advisor, Hugh, had been a Tehran Fellow at UPenn for his PhD, but I didn't know him. He worked with Eugene Nebaichi and some very famous roboticists. And so it was really like this almost divine alignment of the stars that I got to go work with someone who had kind of the same vision. He was obsessed with kind of uncertain geometry and robotics and sensor fusion. How do you combine data from multiple vantage points to get better information about objects in the world? And so navigation was ready to attack with that methodology.
I really like when you said like a divine alignment, that you are curious about this problem in your industry. I'm curious about now, how this is kind of approaching ideas like maybe unorthodox ideas or something just completely new, because there's a tendency that we are afraid to go for risky ideas sometimes. Yeah, how do you see this kind of research direction when you have new ideas as a student, as in your case?
Well,
Do you think there's a risk? Yeah.
I feel flattered that you're saying new, because, you know, as I tried to write my thesis, and even though as I did some early experiments in localization using maps, you know, I'd read all the papers. And you have to remember, this was in the day before Google Scholar, you know, before, you know, ICRA proceedings on the internet. And I remember walking a 10-minute walk, often in the rain in England, down to the library with my stack of 5 pence and 10 pence coins, to go through the conference proceedings and pick out Rodney Brooks's paper and make the copies at the photocopy machine, putting the coins in one by one, and getting that kind of like that single paper, like, you know, his visual map making for a mobile robot. And then you walk back with that precious 8-page paper back to the lab, and you really study every word. And so the nuggets of everything that we did really were in the prior papers. I think Smith, Self, and Cheeseman, and Brooks, and Shatila. And actually, in writing my thesis, it's almost a bit disappointing when I was thinking, like, I thought this was a new idea, but you always have to give credit in the literature where it came from. And so, and it's actually we're part of this wonderful, great community. Perhaps one of the biggest changes now is that back then it was a very small community. So there'd be 3 or 4 papers per year maximum about SLAM in ICRA. You know, and how many papers are about SLAM each year now in ICRA? It's just such a much bigger community. But anyway, I'm very fortunate.
Yeah, I'm glad you mentioned this point of the number of publication. And maybe a quick question here: how do you see this in 30 years? Maybe first of all, the change in Islam, or maybe when it's called now Islam Throw. How do you see the changes in publication and ideas, and just the community is growing? But what is your thought about the publication in general, this amount of publication in this field?
Well,
what is the difference?
Well, there's certainly, you know, a difference in terms of with modern tools, progress can be much more rapid. And it's remarkable that, like I spend a lot of time now on faculty search, trying to hire new faculty for MIT. And we get over 300 applications for one position. And we're looking through across all areas of, say, mechanical engineering. And there'll be a roboticist who is a grad student, they might have 18 papers already. And it's like, how did you write 18 papers as a graduate student? It almost seems unthinkable back from when I was a student. But I think that, you know, I feel the quality of the work is actually very high, you know, in terms of the requirement for something novel on the algorithm side, and some evaluation. Evaluation is a big piece. And obviously using standard data sets like Kitty and so forth. I guess my one regret may be too strong a word, but I wish we had more papers that are using real robots to do something useful in the world. And maybe I'm guilty of the same thing myself, with myself, my students, my postdocs. But it's important to remember that we're roboticists, and we want to create robots that benefit society by doing something in the world. And sometimes to get a paper out, you can process a data set, or but it's not as much using a real robot to do something.
I'm glad you mentioned this point. Why do you think we don't do that? What's you think maybe challenging so far?
I think robots are expensive and hard to access, and sometimes the experimentation is difficult. And in some ways, I don't mean to be critical, but like using the kitty data set, say, to test an idea, it's almost like a path of least resistance to getting a publishable unit out of it. But I think we would be, uh, it would be nice if we had more robots that people could use, and their paper wasn't so much processing someone else's data set. But imagine a conference where the products of the conference are, I'm going to turn my robot on for 10 minutes. And it's what the robot can do in 10 minutes, for example. I don't know.
Yeah, yeah. So maybe I'm curious to ask you in that case, what is thing you think is very promising for SLAM research, or maybe in robotics here in general? What's something you think is very promising, and but maybe as we a community as robotists, we don't give much attention, or we don't consider, or we don't agree with that? What the thing you think is very promising, but we don't give much attention?
Sure. Well, for the first part of your assessment, when I heard the first part of your question, I was thinking it's got to be machine learning, right? So that there's so much potential promise of machine learning. But I think from the last part of your question, in terms of not getting as much attention, it's clear that we are giving a lot of attention to learning techniques in robotics. So I think that if I guess I would, I think that we obviously do need to embrace learning and to try to use the tools that are coming, which there are some of the things happening with deep networks. If you told me 10 years ago, I would say that's magic. How can you do that? But I think maybe what we're not doing as much is letting the robot do some of the hard work. So for example, imagine there's a, imagine situations where the robot, for example, some of the topics my students and I have thought about and thinking about is, as the robot moves around an environment and the world changes, how you can automatically discover objects, because the robot's helping you by, if you say that as the world changes. So maybe the question of how you can operate a robot in a dynamic environment with the robot possibly interacting with the environment, as almost the robot is part of your team doing the experiment, and that the robot learns about the world, and that teaches us about the key problems in robotics. So there's more, I guess we call it at MIT embodied intelligence. In fact, we have a new community of research, embodied intelligence, which Rodney Brooks coined this phrase over 20 years ago. And I think we need more work in which robotics is embodied in a physical system that's turned loose in the world, doing some task, either autonomously or with some human supervision.
And maybe what you think could be technological roadblocks in that case, if you can, imagine what could be challenging so far to achieve embodied intelligence in that case.
Well, one challenge is we still don't have enough good robots. Like I'm saying to my students, I'd love to, can we just get a mobile manipulator and use that as part of our experiment? And maybe a fetch robot costs $100,000. And, robots are still quite expensive. I mean, if you think of something like a Spot robot or an Atlas, which are like, wow, Boston Dynamics, but, I want every grad student to have their own, so Rodney Brooks and others have talked about how the personal computer revolutionized computing. We still don't have the personal robot. I want something that's $3,000 that can interact with objects in the world and do mobile manipulation, and that can be a partner in your research.
I really like this point. Do you think, because we had already an episode yesterday about Boston Dynamics in construction slide, and one of the questions that is really expensive and sometimes is, I don't know how we can reduce the cost, because he said something, we need something like $3,000 and he still can do what he envisioned. Where do you think this is challenging in fabrication, modeling, artificial intelligence, how we can complete this vision in industry, for example, or academia? Because
Great question. I think there's almost a sort of law of supply and demand in terms of how a catch-22 until we have, or SLAM is the great chicken and egg problem, right? Like, which came first, the map or the estimate of the motion of the robot? So I think of a chicken and egg kind of problem of which came first, the marketplace for the cost-effective robots or the cost-effective robots. Like we need the application that enables production in the order of millions of a mobile manipulator. And then, and my hope is that we can find such an application. For example, aging society, folks that are living at home, especially, gosh, in COVID times, imagine if a robot could be an assistant to a person that needs some help. The marketplace is so big with aging society. Could that drive the costs to be down? I think actually, if there were sufficient numbers of production, that the costs could be made small with things like electric propulsion and some of the kind of ideas that say my colleague Sang-Bae Kim at MIT has looked at with thinking about ways to have highly performant electric robots, and of course Boston Dynamics.
Yeah. It's really a really excellent point. And do you think maybe, because in research, for example, do you think you are going in the right direction if we need that vision, for example, to be achieving something beneficial to society? Do you think we are in the same vision recently?
I'd say partly so. I think that we are seeing, for example, I was very heartened by deployments of robots that do the task of cleaning spaces for COVID using ultraviolet light, things like that, where we can do it now and it's beneficial. I think that many of the advances in the component technologies of robotics have come with robots operating in motion capture systems, like some of the early quadrotor experiments and some manipulation tasks. I envision a world where we do not need motion capture systems, and we can use the technologies of SLAM and spatial awareness and spatial intelligence to make motion capture systems unnecessary, because robots just have this sense of where am I and where are the things around me in the world, that they can safely and confidently navigate and interact with people. And so that's why my vision is apt-get install SLAM, that just it's this thing that you just get. And then that enables, then I think we might be able to have robots with sufficient sort of integrity to be operating alongside people.
Yeah, that's a great, Now, I'm also curious to ask you, the thing you think would work out very well, or maybe that's, before deploying in a real robot, but the result wasn't expected or maybe counterintuitive for you, maybe surprising, I don't know. What kind of something you thought would work out very well, that just in empirical world, just in deploying, that just was really, unexpected.
That didn't work, or unexpected
No,
good, or
and maybe
unexpected bad?
because it could be working.
Yeah.
So maybe you thought it would work, it didn't work. Maybe it worked in a surprising way, or you have fascinating result. I don't know, something's maybe surprising.
So I think one of the great things about robotics, and I go back to my hero Rodney Brooks, emergent behavior. When the robot does something you didn't expect. I recall in about 1989, when I was a graduate student in Oxford, in the basement of the Jenkin building where the robotics lab was, I had this experiment going where the robot was navigating around in the very small area, but using SLAM and a common filter, using localization with a common filter with a hand-generated prior map. But the robot was doing data association and some state estimation that it could navigate quite accurately. And I remember running an experiment where the robot was running around and around, and I forgot that the robot was moving, and the robot comes around the corner, nice and slowly, and it's like, oh yeah, you're still going, And so I've had some tremendous emergent behavior stories with underwater robots. So one of the fortunate things in my career, I got to go to MIT in 1991 as a postdoc and joined the MIT Sea Grant Autonomous Underwater Vehicle Lab with James Bellingham. And it's a very long story, but we developed a novel robot called the Odyssey 2 in 1994, which was a low-cost survey autonomous underwater vehicle that we had to take to the Arctic, 200 miles north of the north coast of Alaska. And it had to run its missions untethered and home back into a net for retrieving the robot, homing into a pinger. And we were testing it in a frozen lake in New Hampshire, maybe 18 inches of ice, very cold winter. And our robot, I made a mistake as the programmer, and I programmed the wrong mission, and it wasn't programmed to come back and home into the net. So we lost our robot, and we were all kind of scared and panicked and looking around for it with pingers, drilling holes in the ice. But I commanded another mission to move the robot, and I had accidentally sent the mission that it should have done the last time to do a little survey and home into the net.
Yeah.
And so the robot actually started to do this kind of crazy, what seemed crazy survey pattern, and we were getting more depressed that a robot, what's it doing? And then I remember we had a wonderful French postdoc, Jérôme Wagenet, and he went back to our net, to our tents, to get his computers and compass or something. And the robot had homed into the net autonomously, and it was exactly where it should have been from the previous mission.
Yeah.
And he's like shouting on the radio, "It's in the net, it's in the net, it's in the net." And so we thought we'd lost our robot and we'd all lose our jobs because this is an expensive thing. And the robot emergently decided to do the right thing and go back home.
That's, yeah, I think fascinating story. Yeah. Just about emergent behavior and robotics. Yeah. So maybe in this 30 years, what's something you think in robotics maybe changing? Yeah, because I think when, 30 years ago, I don't know how it was. Yeah, this kind of challenges or ideas, or what is next we have to do. What did change in 30 years till now? How do you see the progress in general? And maybe still, yeah.
No, sorry. I can think of lots of things technologically. One thing I want to point out is diversity. I'm a big fan of diversity and increasing participation of women and underrepresented minorities in robotics. And I see many strong female and underrepresented minority roboticists, many more than I had seen a long time ago. And for example, at MIT, I was recently in a PhD committee meeting where the PhD student was a woman, 3 other faculty were all women. I was the only man in the room. That's changed in 30 years in a good way. In terms of technologically, I think that it's hard to, obviously having GPUs and deep learning and sort of this massive amounts of computation available is kind of game changing. But I think what concerns me is that we still have the question of robustness. How do you truly sort of trust that a system's going to work? And it's a little easy to somehow make your video or choose your results from when things kind of work well. But in practice, there's sort of an ROC curve. There's a receiver operating characteristic curve that says the false positives versus false negatives. And there's going to be times when things don't necessarily work. So what I would say in terms of things that I start to see changing, work, for example, my former student David Rosen at MIT and Luca Carlone, my colleague on the faculty, of certifiable perception. So algorithms that can self-certify their results in certain situations. So I would love us to be able to develop systems that can self-certify the kind of outputs of their decisions or verify their assumptions, so that then we could trust the integration of those components into larger systems, that it would do the right thing and be safe around people.
Yeah, I agree with you. But I think here's a question a student can ask about the problem of robustness as well, how to make sure it's robust. Do you think that's something because of the pressure that you have to get results sometimes? Yeah, recently we have to pressure, as you mentioned, you have to just working for the first time, but we don't invest a lot of time about making sure it's robust and reproducible and the performance as well. Do you think there's a problem here? Where it's come from, essentially?
Well, I think it's a problem and it's an opportunity. And I mean, I've been myself, pushing at the paper deadline, trying to get things to work. And, and I think we really were in a phase in robotics, maybe 30 years ago, 20 years ago, where getting it to work once, getting the figure, getting the movie, that, that was an achievement. I think the question of how do you show the ability to operate under a wider set of conditions, and show where your algorithm fails, that's important. I mean, as we, there are movements, for example, posting code on like papers with code. Imagine a world where we have, it's not even, there's like a standard robot. So imagine there's a $3,000 multi-arm manipulating walking robot that we all have. And you could basically, your paper includes a sort of a code that's sort of like almost like something that, maybe on a USB stick kind of thing that you could just punch it into a robot and it will duplicate the same performance. So I guess it's really reproducibility
Mm.
and open access. But the thing that's unique about robotics is that it's in the physical world. So in say CVPR or computer vision conferences, you could say, okay, here's my code and you can apply it to this kitty data set and get this number and that's all good. But how do we go beyond like a static data set to a closed loop robot where it's like, if you load my code on your robot and it will
Mm-hmm.
pick up your coffee mug, and put it back where it belongs,
Yeah.
something like that.
Yeah. I agree with you. Yeah. So maybe here's a quick question about maybe what is still maybe unsolvable dilemma, for example, for SLAM and robotics or marine robotics, because I think this also still a very interesting topic as well. So what could be still unsolvable dilemma or still challenging for you as well?
Sure. I feel that there's one thing that we make a lot of assumptions, and I'll go back to Rodney Brooks again.
Yeah. Okay.
We question the assumptions and negate the assumptions and see how our methods fail. So for example, implicitly still, we assume for a lot of times that the environment is static and that the environment doesn't change. So can we make techniques that are truly robust to the environment changing? And in terms of a dilemma, I think there's almost a form of like Heisenberg uncertainty principle about dynamic environments. That's kind of the question, am I lost or has the world changed? So imagine a robot that goes back to where it thinks it started, everything's changed, and it's like, am I lost or did the world change? And then how could it actively decide, well, why don't I go back in time and say, well, what did I expect to find? For example, when we looked at experiments in dynamic environments, for example, trying to use place recognition based on objects in the world, it's actually kind of tricky. Like what parts of the environment can you assume that don't move very often, like furniture? What parts move a lot, like coffee cups? And how do you, could you build up a kind of semantic spatial awareness of understanding the world in terms of objects and still knowing about places,
Yeah, that's also a good point. Yeah. So maybe we can go for the audience question because we have a lot of questions, especially from Reddit machine learning community. So the first question is from Ronnie. He is from University of California. And he said that what are the best or what are the least developed research topics or overlooked research that you think is important for success of robotics?
Great. Let's see. Well, I think if gosh, on in my own kind of research group's trajectory, I'm going to go back to this question of robustness and certifiable. Can we really trust the answer? I'm going to go to the question of semantic representation. How do you represent the world in terms of objects and places and in kind of more human level terms, while still coupling to the kind of metrical ability to locate accurately and so forth. I think in the underwater domain, which I think a lot about and hope to do more work in the near future, the issue of how you communicate is very hard. We have very limited communication links, acoustic links and optical links. And it raises the question of how do you have resource constrained robots that may have limited power or limited kind of sensing ranges, sensing capabilities, and limited communications to a human operator. So I think that that's a whole sort of portfolio of questions that we're trying to think about. But more generally, I have I'm very fortunate that in addition to my MIT career, I went on sabbatical and remain a technical advisor at Toyota Research Institute, where we're working on self-driving cars and active safety technology for cars. And one thing that experience has taught me in terms of open research questions is that the interaction with the human is absolutely critical. So for autonomous driving or highly automated driving, how do you predict the actions of agents in the world and understand the intent of other drivers and pedestrians and road users like bicyclists and the own driver? So I think that there's a huge space of opportunity where robots meet humans, specifically with respect to prediction, anticipating what will come next, and coupling that to estimating risk, and then connecting that to motion planning and so on. So it's actually, despite the tremendous growth in the field and so many papers and, there's still a lot of really big challenges.
Yeah. Thank you for this answer. Yeah. And we have another question also. Yeah, maybe we can get this question. For publishing research, not in top ranked labs, what's your advice in getting attention to your work in such a competitive and top heavy field? Or is it just another way of asking, how can I write compelling papers?
Sure. Well, I would say, first of all, I very much believe in the democratization of research, that you don't have to be at MIT, Stanford, or Berkeley to be publishing top papers. And I'm very fortunate that I have dear colleagues who've truly taught me things and moved the needle on their fields, and universities all over the globe, and I could, places in Spain and Ireland and Germany and Australia, and places that are not, what you would say is, I think we can all participate and we can all contribute. I think that, and also submitting to conferences that are double blind so that the authors aren't named, and that, my hope is that folks would feel that everyone is welcome. Good ideas are always welcome. I think there are some researchers have posted talks about how to write a good paper or make an impact. For example, my colleague Bill Freeman at MIT, he's written, you can find it with Google, a talk about what makes a good CVPR paper. And he, one of my colleagues just referred me to that yesterday, because the CVPR review came out and they're very challenging. And I think that some of the, I think that several things. So in some ways, there is a lot of there's a stochastic nature to research. How does an idea resonate with the reviewers? But I think that if you can try to, it's hard, but impact comes from the papers that really have that kind of novelty aspect, which is hard to sort of distinguish or capture. And I think that let's see, I would say that if knowing the literature is just so important, and and with Google Scholar, there's easy to get many things, but then also so much new things appearing. So I think one of the best rules I would say for writing good papers is to spend a lot of your time reading good papers.
Yeah, that's a good point. Yeah. And we also have a question from Herbert. He's a student at Warsaw University of Technology. What's your opinion, the best tool or skills to learn or to begin fastly, this fastly changing technology branch? What kind of tools or skills?
Sure. I think one of the things that's challenging about being in a robotics lab today as a graduate student is it's so much work it's so challenging to get everything to work. The whole like apt-get install PhD, how you figure out how ROS or something like LCM works, or Moose, how you get device drivers for cameras working, how you install GTSM, how you write GPU code. I think one of the things I tell my students, because I'm, things like faculty search committee meetings and teaching and various sorts of demands, is that you're not actually going to learn that much from me. You're going to learn from your fellow students, which is something that's actually very hard with COVID, that the students aren't in the lab able to physically interact. But that one of the true benefits of a place like MIT, Stanford, Berkeley, et cetera, Georgia Tech, where UPenn, where you have Michigan, where you have a community of people, you can, by being present in the lab and engaged, you can pick up a lot of those skills of other, how to get things done as a roboticist. And you have to combine that with understanding the algorithms, and work, but it's, and performing careful experiments. So I guess it's you will learn gradually, and you'll learn from everyone you meet. Think of every person you meet in your lab and in colleagues' labs as a potential co-author, a potential collaborator. I think actually one of the most wonderful things I feel about my career is I feel very fortunate that the people I've worked with are so amazing and taught me so much, that it's really, I have a saying, success is infinitely divisible. You know, if you do
Mhm.
something that's truly successful and you have 2 co-authors versus 1 co-author versus 7 co-authors, I don't care how many co-authors are on the paper if it's a
Mm.
sufficiently good paper. So you're going to make yourself better by working with other people, and what you give in helping them will come back multiplied from the help other people will give you.
Yeah, I agree with you. Yeah. And here's also a question from Sanskar. He's asking you, I'm looking to get into postgraduate computer science program in MIT next year. How to get into research and deep learning? I am self-taught and I have no idea how to start or go toward writing my paper.
Sure. Well, first of all, the thing I tell everyone is apply to many schools. Sadly, we get hundreds of applications for these programs. And
Yeah.
so if you, you know, it's, you know, I would apply to very many schools. There are some fantastic schools. It doesn't have to be MIT, Stanford, Berkeley. Um, Learning skills, I think we're fortunate that there's some wonderful courses online. MIT has open courseware historically, and then recently as part of edX, there's obviously Coursera and Udacity. And I think that if you if you look, and feel free to email me, jleonard@mit.edu. I try to answer all my email, try to point you towards things in a specific area. But I think that in particular for deep learning, like at MIT, Lex Friedman, who has quite a notable podcast. He
Yeah.
previously taught a deep learning class at MIT with some resources. And if you're persistent and you dig online, you should be able to find some video lectures and things. But ultimately, you have to write your own code and do something. And you know, I just be persistent
Yeah.
and just try to learn. Be always learning.
Awesome. Yeah. And we have also a question about, yeah, what are the challenges that are unique to SLAM for marine environment? And what are the some of interesting things that you have been doing to address this issue?
Great. Well, so one thing that's we don't have. It's hard to see underwater, and so dealing
Mhm.
and sensors such as sonars can be very challenging to interpret, and good sonars can be expensive. So you have your kind of size, weight, and power constraints that are very much multiplied, and you have environmental factors. You know, the waves, the currents. Um, you know, I'll be honest. I've done less marine robotics than I would have liked in the last kind of roughly 8 to 10 years due to being associate department head and various sort of endeavors. But I have a crop of new students in the MIT Woods Hole Joint Program, which is a small but really quality program. And we're looking at cooperative navigation in multiple vehicles. And we're trying to do semantic SLAM, like based more on object, combining machine learning and object recognition with SLAM for underwater applications. And we're also trying to think about how humans and robots might work together in a marine environment. Um, from a more algorithmic perspective, I go back to David Rosen, my recent postdoc, who this certifiable approach to SLAM. I think that if we can, that can really benefit us underwater, because sometimes for a terrestrial application, for example, for self-driving cars, many approaches, such as Google's, they've said publicly, now Waymo, but they would make a very precise map by driving the car around the environment in advance. And so you're assuming that the world is not going to change too much. And then when you make the map that then the car is then going to use to accurately localize itself, you can, it's possible for a human to verify the map and say, you know
Mhm.
what, the algorithm messed up here, or this changed. Maybe there were leaves on the ground blocking the lines, something. Underwater, we don't have a human that can go in and intervene. So
Mm.
that's why resource constraints and robustness certifiability are extremely important for underwater, because it's not easy to have a human that sort of says everything's okay.
Yeah, great. We have a lot of questions. Maybe we can make two. Yeah, why we don't have useful autonomous robots in real world yet? I think we covered part of that, but if you want to add some point for that.
Well, I guess I called out the cost issue earlier,
Yeah, yeah,
but also I think that, you know, it's, if you look at the success of something like the Roomba, you know, again,
yeah.
Rodney Burks, you know, it's low cost and has a simplicity and a safety to it. Is there an application, you know, like cleaning up the dishes or something that will enable that, you know,
Hmm.
until we find the application that causes the creation of 1 million robots for your house, say 1 million mobile robots with manipulation capabilities, for example, it is this catch-22 that without the demand, we can't make the supply. I think that, yeah. But I'm optimistic. There's a lot of great entrepreneurs out there, and I think there's opportunity.
Great. And also here's, maybe we can take this last question here from the audience. What is the most important open problem in AI? And maybe what is also could be very maybe interesting application so far you see applied by AI? Yeah.
Wow, I feel almost unqualified to attempt an answer, but I would say the issue of explainability, which couples, I think, to robustness, so that it's one thing to know something, it's another thing to know that you know something. And so that sort of meta understanding of a problem, folks have written that machine learning AI competences can be very narrow, like the ability to recognize objects. And if we were truly to achieve a certain generalized capability for intelligence, I believe it will have an explainable component, so that it's able to kind of verify when it knows and doesn't know something. And I'm nervous about black boxes, that we can't understand what's happening inside them.
Yeah. I think this question also may be related here from the audience as well. What are advantages or disadvantages of AI and robotics research in academia versus industry?
Great. It's easy to think that all the actions in industry, and they have huge budgets for their Amazon cloud bill, and they can do massive experiments and evaluations, and they have so much access to data. And it's easy to say, well, why would a professor, an assistant professor that did their PhD 2 years ago, and they have 4 students in their lab, and they maybe got 1 robot and they're building their lab, how could they compete with Google, Amazon, Facebook, that have massive budgets and massive manpower? But I think that history has shown that there's something kind of almost magical about the faculty member, especially a junior faculty member, and some 7 students and a postdoc, just that the ability to think a little out of the box or somewhat creatively about a problem, that we still need professors, we still need young people to choose academic careers and to be teachers, and that I think history has shown, and the future will still tell, that even in AI, with all this machine learning, and that the humble grad student toiling away in the lab late at night can still make a difference and have the breakthrough idea.
Yeah, I agree with you. Yeah. So we are closing to end. I have a few questions. The first one, what could be crazy ideas you still have in your mind? Yeah, after 30 years, how you keep this passion and, oh, I need maybe crazy ideas.
Well, let's see. I feel fortunate that I'm still obsessed with this problem. Maybe it's fault. Maybe the world has passed me by, and I'm like, just move on. Everything's going to be a deep network, and train it end to end, and don't think about what's happening in the middle. But I think that for example, a lot of our inference techniques are based on the assumption of Gaussian distributions. And in that framework, we have very sophisticated techniques like GTSAM, ISAM2, but the real world has many situations where the errors are not Gaussian. For example, underwater, using ranging measurements and sonars, situations with lots of data association and ambiguity, and using the output, say, of machine learning detectors that are sometimes very good results, but sometimes very bad results. And so when you try to use a more generalized non-Gaussian representation of uncertainty, for example, a mixture of Gaussians or a sum of Gaussians or some more general distribution of particles, it turns out that our techniques for inference don't scale very well. For example, data association and mixtures of Gaussians representations have the curse of dimensionality rears its ugly head. You have a mixed hybrid discrete continuous optimization problem where things will kind of blow up computationally. And so in some ways we're walking on a tightrope, and if there's a very strong wind, we get blown off the tightrope. there's the frontier of what we can do seems very big, but the boundary is still, I can tell you a problem. Give me a robot and I will show you how to make that robot fail.
Yeah, that's also excellent. Yeah. So maybe I'm curious to ask you, since you are a really successful robotist, is there any moment, any moment do you feel like, yeah, failure? And maybe it was delusional for you. And yeah, I'm curious about this moment, because I think that's something we need to know about. Were there a moment for you that's,
I
oh,
feel failure every day. I, I get, things are
what?
hard to make them work. We get
Yeah.
papers rejected from ICRA, from CVPR. Sometimes we have a goal to submit a paper for the deadline and we don't quite make it. And we say, you know what, we're going to save this for the next paper deadline. I think if you, I think that it's, in the past we've lost robots and been
Mm,
fortunate to find them underwater. The DARPA challenge, Urban Challenge, our robot got in a crash with the Cornell robot, and as well as at least one other robot. And these would be embarrassing events in the right context. But I think we have to remember that we're all human, and
hmm.
humans make mistakes, robots make mistakes,
That's
and
a good.
and if you're not getting papers sometimes rejected, you're not pushing yourself enough, in the sense of, there's a lot of smart people out there all over the world, and we're fortunate that we get to work in such a creative and ambitious and challenging
Hmm.
area. But I am often I'm very tough on myself, actually. I think
Hmm.
I so much I wish I could have done, so
Yeah,
there's always more work to be done.
indeed. Yeah. And maybe what could be something you learned from DARPA challenge or challenge in 2007 till now? We could be lessons. Yeah.
What I would say, we really had an amazing team, and the
Mhm.
people on our team in that team photo, like where they are now, is it's amazing. And so there's some sadness, for people not longer with us. But the if when we work together, we do amazing things.
Yeah.
Even though we had many strong personalities and certain people fought very hard with other people because of genuine intellectual differences about how to code this or that and how to model this or that. Um, by working together and bringing that diversity as a strength of bringing many viewpoints together, even if you don't win the competition, we finished fourth place, or you know
Yeah.
uh, maybe fifth place, if depending on, talk to UPenn, who is very ambiguous ending, but that and I love those guys, but that you can still win even if you don't finish in first place.
Hmm.
The benefits of participating and working together have paid dividends
Hmm.
manyfold to my colleagues like Jonathan Howe, Emilio Fazzoli, Carl Agnema, Sertaj Karaman, Edwin Olson. I run through the list of the people that we had in our team. Um, they've gone on to do great things.
Yeah. Yeah. And do you think ego is important for the researcher when you have no
Um,
ideas? Yeah.
the ego. I feel almost like I'm an anti-ego. Like everyone around me is smarter than me. There's a book about MIT, one of the college guidebooks. Then starts off, it describes every university in the country and some
Yeah.
around the world in a few pages, and it opens its something guide to colleges. But the opening for MIT is no place provides a greater assault on the ego like MIT. That everyone around is smarter than you. I'm sure it's the same at Berkeley or Stanford or Oxford, etc. But that when you surround yourself with people, one
Hmm.
of the first things you have to realize is you don't know everything, and the goal is not to try to show that you're smarter than the people around you. The goal is to learn from the people around you.
That's a good point. Maybe also there's a question here: what it takes to be a successful robotist? For example, you mentioned if everyone smarter than you. Do you think thinking differently to be different? Because, for example, if we speak the history of an AI, for example, some researchers were considered pariah for a long time
Yeah.
because they have different idea. So do you think it takes to be smarter? Of course, you have to learn from everyone. We learn, but it takes you to think differently as well. Do you think, if you think
Yeah.
different way?
Yeah, I think I would say to thine own self be true. Like keep
Mm,
your, personal, like I have, um, I have colleagues that have a very different outlook on the world than me, but I
mm,
don't expect them to change to be like me. And we all should be flexible and we should be open to new ideas. Um, but I think it's for example, I would say that I've always wanted to do more work that combines SLAM and perception with motion planning and kind of closes the loop, and we've done some work in that area. But I think I realized that there's a way that folks that work in motion planning, like Sartesh Karaman or Emilia Frizzoli or Steve Laval, there's a way that they think about the world, Lydia Kavraki, that I acknowledge is a different way than I think. And
mm,
so, and our community is better because of the way that they think, in the sense that there's these different subdisciplines. And so we should embrace that intellectual diversity of the different ways of thinking. And so for an individual, sometimes you have to be flexible and give up on,
mm.
some of your favorite little hobby horse kind of ideas. But you should also feel free to be true to yourself and your own view.
Yeah, yeah, that's a good point. Yeah. And what is maybe the most favorite book inspired you have ever read?
Wow. I love The Great Gatsby,
Hmm.
but in Robotics Switchbook for robotics,
That's okay.
uh,
I mean,
yeah.
if you can tell.
The book Tracking and Data Association by Yakov Barshalom that came out in 1988 was really influential on my thesis because that talked about tracking and data association, it sort of common filtering and multiple hypothesis tracking, and that really helped. I think that was probably, if you take Rodney Brooks's papers, Smith, Selfin, Cheeseman, Rajesh Yatila's papers,
Mm,
Philippe Moutellier, and then add in Barshalom's Tracking and Data Association, pretty maybe Ken Stewart's underwater sonar thesis,
yeah.
a couple other, like I can almost picture the literature tree, but those
Mhm.
early things, like put those together, that kind of made me who I am. And,
Yeah.
and in some ways, like I wrote probably one of the first SLAM PhD theses, you could argue, but there have been now dozens, if not hundreds. And so I feel like I'm part of this family, and I
Yeah.
still get excited when I read a new
Yeah.
PhD thesis about SLAM.
Yeah.
So
Yeah.
I'm
Okay.
crazy. I need to do something different.
I like that, just to make them different. Yeah. But maybe what is your aspiration? What's something you still aspire? Maybe in the life and also as a robotist as well. What's your aspiration?
Let's see. I aspire for diversity,
Yeah.
increased participation of all people, and I aspire for peace, and I aspire for um, just inclusion, and I aspire for myself. I guess it would be great if we had more of a curriculum for robotics that was accessible
Mm,
to a broader group, like a physical
yeah.
curriculum where instead of buying a textbook, you buy a robot and the robot teaches
Yeah.
you robotics. So
That's one.
anyway,
Yeah.
all right, maybe I might need to
Yeah.
go. You're asking a lot of great questions. You're wearing me out.
Yeah. And maybe what is maybe the most important quality you have gained being in academia? One important quality you have to maintain.
I think you have to respect. I think
Mm,
um, I every interaction in an academic environment, the starting point is respect. And you think about all the obstacles that folks overcame to get into that position.
yeah.
Highly competitive undergraduate admissions, highly competitive graduate admissions, highly competitive faculty search. Um, sometimes I see colleagues that get very emotional and fight with one another and maybe don't even talk to each other after,
Yeah.
some misunderstanding on a grant proposal. And I think that uh, we have to say that every member of the community it deserves respect and
Yeah.
we're all in this together. And that to me is a really important quality.
Yeah. That's a great message. Yeah. And lastly, what was the best advice was given to you and was a life changing? Yeah.
Well, the best advice I got, I didn't follow it, but
Uh-huh.
I understand it better. When I was a junior faculty member in 1996, I was starting out as an ocean engineering professor, small department, and all the pressures of being under for junior faculty in the tenure process. And Professor Eric Grimson from MIT, a famous computer vision researcher, he said his number one piece of advice was just have fun.
Mm.
And all the worrying about this or that, just have fun, do what you think is fun. And I didn't initially follow it too well, but then I shifted to that policy, and things worked out for me pretty well. And so try to have fun with what you're doing. That's we tried to joke a bit in my lab, and I think keeping the sense of humor, having fun is important. Doesn't all have to be serious, as long as it's respectful.
I really like this advice. Yeah, I really like it so much. Do you have any final words you would like to say for robotics community audience listening to you? Any final words?
Thank you. Just thank you for listening, and remember how lucky we all are to work on such a great problem with such great people. And if you're young and you're trying to decide on an academic career, it's challenging, but it has wonderful benefits. And I look back to all the, meeting academics at the lunch of an ICRA or an IROS in Brussels or in Spain, or and how the friendships foster over the years. And now, some of my dearest friends in the world are roboticists that I know from all over the world. And so, I guess I would say that if an objective in life is to if we're fortunate, we can make many friends, and robotics is a great place to make friends.
So yeah, thank you once again, Professor John. It was such an honor and a pleasure and fun to listening to you. And yeah, you're really a great representative. Thank you for once again for your time. I appreciate it.
You're too kind. Thank you. Bye-bye.
Thank you. Okay, thank you, Professor. Thank you.